We'll start the course by introducing Maxwell's equations that are the fundamental framework for electromagnetics, optics, and photonics. Maxwell's time-dependent equations describe the interactions between electric field, magnetic field, magnetic flux density, displacement, current density, and charge density. These fields are vector fields that are governed by Faraday's law, Ampere's law, Gauss' law, and Gauss' law for magnetism. For continuous signals, we often assume that they have harmonic time dependence. This can be included by introducing a complex phasor. In this case, the time derivatives in Maxwell's equations can be written as often we don't need all the vector components. Then it's useful to decompose the different components. The curls of the vector fields can be written in a determinant form like this, and from this decomposition we can relate the different components of the magnetic field to the electric field and vice versa. Let's take an example. We have an electric field that has only the EX component along the UX unit vector. Then we can write the curl equation of the electric field, and here we multiply the components from here to here, which is 0, along the unit vector in y direction. We have the first component along the UZ, we have again 0, and in this direction we have the component along Z direction. And this can be related to the magnetic field, which is in component form. And now we can relate the components along y direction. So the y component of the magnetic field can be calculated from the derivative of the EX component along the Z direction, and the magnetic field in Z direction can be calculated from the derivative of the EX component to the y direction. So this component form is useful in finding the full components of the fields, and this is especially useful in optical thin films and waveguides when we are seeking the full fields within these structures.